and I operate by d squared plus 1. Yeah? What happens to d squared plus 1 cosine t? Well, this is 0. And all of a sudden, what do I got? I've got d squared plus 1 squared acting on y equals to 0, right? But what's that? That is lambda equals to plus or minus I twice. And we know how to solve that. What is the solution? It's y equals to c1 cosine t plus c2 sine t plus c3 t cosine t plus c4 t sine t. I already know what this is. This is the homogeneous solution, right? That's the homogeneous solution. We already know that's part of the general solution to the original problem. What's that next bit? That is the form of the particular solution that I'm looking for. So this improves my naive guess. I take this and I say, aha! I should make yp, so I think this requires thinking. I think yp should be at cos t plus bt sine t. Maybe this will work for a particular solution. In fact, there's a theorem that says that will form the particular solution, but let's actually work it out because we're not done until we find the a and the b, right? Fortunately, this class goes until 1 o'clock, so I got plenty of time. Let's see here. What? No? No? Okay. I know, I still think the joke is funny. Let's see here. You can disagree. All right, so we just figured out that we want to make, and you guys, can you think of a way to make this nicer to work with? Well, I guess I can leave it like that. I don't know. I mean, I might sometimes factor out the t. I don't know. I'll just leave it like it is, at cosine t. I debate whether or not it's worth factoring the t out. Some people factor the t out. So we got to calculate yp prime. And product rule is important there, right? So we got a cosine t minus t sine t. Product rule. And then product rule again. Sine t plus t cosine t. Definitely worth your time to group sine and cosine at this point in the calculation, because otherwise, like, you get comparatively more product rules. So let's put all the cosine t stuff together. I've got cosine t times what? I got myself an a. What else is cosine t? Plus bt, yeah? And then sine t, what do I got with sine t? Looks like I've got a minus ta here, right? And also a plus b, yeah? What do I have to, my goal is to plug it back into the differential equation to figure out what a and b have to be to make this to work. So I need to differentiate another time, right? Need to differentiate it yet again. So yp prime prime equals to, well, minus sine t, a plus bt, plus b cosine t, plus cosine t, minus ta plus b, plus, well, rather minus a sine t. Again, I would encourage you to, clean things up here, tidy things up a little bit. Yp prime prime is what? I've got a cosine t times what? b plus b minus ta plus sine t times what? Looks like we got a minus a minus bt, right? Minus a. Now we plug it into the differential equation. Now substitute into the differential equation. So yp prime prime plus yp equal to cosine t. What do we get? We get what I just had above, right? Which is cosine t 2b minus ta plus sine t of minus 2a minus bt, right? And then what was yp? Yp was at cosine t plus bt sine t. All of this is supposed to be equal to cosine t. If we did this right, something magical happens now. This term cancels with this term. And the at cosine t term cancels with the minus ta cosine term. At which point, we can equate coefficients because we've got cosine t weighted against a cosine and a sine over there, right? So using linear independence of sine and cosine, we can equate coefficients of sine and cosine. We can equate coefficients of sine and cosine. So like, I'll write down cosine t. What's the cosine t equation from the above? Cosine t, I've got 2b equals to how many cosines over here? You got one of them, right? There's one cosine plus 0 times sine t. I don't know if you can see it's there, but there it is, 0 times sine t. So 2b equals to 1. And minus 2a equals to 0. So we have determined our undetermined coefficients. Our job here is almost done. A equals to 0. B is equal to a half. Hooray. We can put those back in to the y sub p, and we have now found an honest-to-goodness particular solution. And as such, we can write the general solution. What's the general solution? We've got our c1 cosine t plus c2 sine t. That's the homogeneous part of the solution. And then plus 1/2 t sine t. And there you go. So what's the method of annihilator's role in all of this? What is this thing we're doing? The method of annihilators doesn't solve the problem for you. What it does is it gives you a path to derive the particular solution's form. It showed me that I should put a t times cosine and sine to find the form of the particular solution. All right? Now, there's a way of presenting this material without actually covering this way of thinking. Like I've taught this in Calculus 2 at NC State as a graduate student. We don't talk about differential operators in there. We just say things like, there's overlap. This is our way to sell it. There's an overlap between the forcing function, which is cosine t, right, and the homogeneous solutions, cosine sine. So basically the mantra is this: when you have overlap, you multiply by t in the particular solution in order to make it work. So you take the naive solution and you multiply by t. And that's kind of good off-the-cuff advice, but it also is notoriously tricky to interpret when you get a few more moving pieces, because sometimes you multiply part of the particular solution by t, but not the whole thing. And so to the actual structure of how you construct the particular solution, the nuances there. These are all folded into this universal overarching calculational technique called the method of annihilators. So that's why I teach it, is because it gives a way of understanding where these things are coming from. They're just not a black box. You need some understanding. And also, it's just good to invest time and energy into understanding what operators are and how to work with them. Now, let's talk about this. What is this equation? Let's take a step back. What we're looking at here is something like a spring mass problem, right? So you got a mass, you got a spring. So the mass is equal to 1, the spring constant's equal to 1. And what's the force? You know, basically you've Mr. Top Hat over here or whatever. And he's got his cane. And he's the mass, right? He's poking it back, and pushing it and pulling it, pushing it and pulling it. Because that the force, cosine t, it's sometimes positive, sometimes negative. That means it's a pushing and pulling force, right? Pushing, pulling, pushing, pulling. And how is he pushing and pulling this spring system? He's pushing and pulling it at this natural frequency of the system, right? What happens as t goes to infinity in my solution? I mean, sine and cosine, they stay bounded. Whatever that is, that part just keeps oscillating however it did start, right? That's the sort of the initial condition. But this thing over here, that gets really, really big in both the positive and negative sense. And this picture is really hard to interpret once that gets going, right? I mean, the fact of the matter is that the mass is going to smash into the wall long before t goes to infinity, right? But what's happening here is pure resonance. The energy is building up to infinity, and of course the spring is going to break, right? So if you have a system like this, a pure mass spring system with no friction, you can have this kind of pure resonance, right? This is also possible in like an LC circuit. If you talk about RLC circuits, inductance and capacitance, an LC circuit is much like, it's the electrical analog of the spring mass problem. And in an LC circuit, you can also have this kind of pure resonance, right? But that's an idealization. Is there any such thing as a circuit without resistance? Not really. There's always resistance, right? So there's always friction in a real physical system. So a much more complicated question, an interesting question is, if you have a spring mass system with friction, right, then what is the frequency, if you have a push-pull force, if you've got a sinusoidal force and you attach it to the system, what frequency of the force attached will result in the maximum amplitude response? We still call that resonance, but that's not pure resonance, and that's something I will probably work out for you guys another day. It takes me about a half hour to work out the calculus of that, but we can do it with the tools we have at our disposal in here. And that, of course, would be interesting if you were actually building something like a receiver, right? You have like radio waves going through air. You want them to get picked up in some kind of circuit, RLC circuit, such that you amplify those waves and you can hear what people are saying over the radio. So if you wanted to tune that circuit, you'd want to match you want to have the circuit match the resonant. You want it to be resonant with the wave that you're trying to catch. So anyway, these questions are of course interesting. And anyway, we are to give you a. I'm sorry, I'm out over time, but one more thought. Two methods we're going to look at here. The oneness method of undetermined coefficients. I've shown you an easy example and a moderate example. I'll show you some more examples next time. The other method for solving the non-homogeneous problem is called variation of parameters, which involves integration but is totally general. So we'll look at both next time. Yep. Don't be frightened. I only test the n equals 2 variation of parameters. N equals 3 and larger is in my notes. But it is too horrible for in-class tests. It is truly, maybe a quiz question, but you got it?